last speaker, and so from now on, everybody gets to introduce themselves again. So anyway, it's my pleasure to introduce Olivier Dudas from Paris, who is going to speak on representations of finite reductive groups from characteristic 0 to transverse characteristic.
Thank you. Thanks very much. It's really a pleasure to be here. So today, actually, I won't talk about anything specific to groups of Lie type or finite reductive groups. It would be more elementary and focused on what Radha talked about yesterday at the end of her talk, namely the decomposition number. So what I want to do during this series of talks is to focus on not on the whole category of representation of the finite group, but just some numerical invariants. Invariants for representations of a finite group G. And by that, I mean, as an example, the number of isomorphism classes of irreducible representation. Okay, so it could be either in characteristic 0 over C, for example, for complex representation. So we usually talk about ordinary representations or ordinary characters in that case. But also in characteristic, positive characteristics, so characteristic L, and at least for the irreducible ones, talk about the Brouwer characters. Okay. What I want to understand and to explain as well is the relation between the two, so how you pass from the characteristic 0 to the characteristic L, which I would refer to as the L reduction, which will be from characteristic 0 to characteristic L. And there is a somehow dual process, which is going from characteristic L to characteristic 0, which I will call lifting representations. So now it's from the positive characteristic to the characteristic 0. Okay, and this will be encoded in the decomposition numbers or decomposition map that Radha mentioned yesterday. Okay, so that's, maybe another way of saying this is if you really want to understand the representation of this group over some field, you can, so if I follow the notation, you can try to understand the module, the finite generality modules or KG modules, which means if you want to understand the category, you have to understand, of course, the objects, the modules themselves, but also the maps between the two, the extensions, and so on. Okay, but I won't actually look at any kind of homological aspect, morphisms or extensions. I will just focus on the Grothendieck group of this category. When you forget the extensions, okay, which means all the exact sequence, short exact sequence will be split. Yes. Okay, so that will really be the main concern of this series of talks, and also the relation between different Grothendieck groups for different categories, different characteristics. Okay, when you're studying categories, you have functors between them, and when you have sufficiently nice functors, they will induce linear maps at the level of Grothendieck groups, and these are the kind of maps that I want to study. Okay, so there is one thing specific that I have to mention for groups of Lie type. So for finite groups of Lie type. And this was very important in Meinhoff's lecture this morning, is that there is a geometric construction of the representations. And by means of what? Of some L-adic cohomology of a variety. So something with coefficient in QL or QL bar, this L-adic ring, or its algebraic closure. But so this is really very difficult to compute, or even very difficult to define. I won't say anything about this. But the good point to make is that you could actually change that field of coefficient and replace this field of characteristic 0 with some finite field of characteristic L or algebraic closure here. Okay, so that's very something important in everything I'm going to talk about. There is, for this geometric construction, there is a priori a way to go from characteristic 0 to characteristic L via this cohomology. Okay, so that will be the point of these lectures, and all the methods that I'm going to talk about during the last lectures, they rely on these constructions. Okay, so I can tell you a bit about the plan of the lecture. So today, as I said, I will not talk about anything geometric, not anything specific to reductive groups. Just introduce the decomposition matrices or decomposition numbers and the basic sets. Then I will explain the case of finite reductive groups. How you can fit the theory that Meinhof has explained with this Deligne Lusztig characters, this like graph that he has defined between the encoding the different scalar product with the characters. When you can fit this theory into the modular framework, so into the block theory, for example. And in the last lecture, I will explain and will give some methods to compute the decomposition matrices. Some of them will be conjectural, but very suited to computation using some computer and the Chevy program that Meinhof showed you this morning. Okay, so let me just recall a little bit about what Rada said yesterday. So G will be my finite group, so any finite group at the moment. And I have to fix a prime number which will represent the characteristic of the representations, the coefficient field. And I have to, unfortunately, I cannot use P. I have to use L as a prime number. And this is because when you use this geometric construction, if you look at the cohomology over QP, usually it means really the equal characteristic. It's a different theory that I won't use. So I really need this prime number L to be different from the characteristic of all the algebraic varieties, algebraic groups that will be involved. Okay, that's why I really need a different notation. Sorry for that. And since I will work both in characteristic 0 and characteristic L, I will fix some L modular system. So that was constructed yesterday by Rada. So you can fit it in the following picture. You have your field of L-adic numbers, some extension K, so which will be a field of characteristic 0. Inside, you have the L-adic integers. You can look at the integers of K over ZL, this O. This will be some local ring, which will have some residue field K, which will be some extension of FL. Okay, so in Rada's talk, actually that was the algebraic closure of FL, but I would not need that. I just need this extension to be big enough, and this one as well. So all the representation that will be defined, they will be all the irreducible ones will be absolutely irreducible over the extension. So the only thing that I should do is adding some roots of unity with respect to the order of elements of the group G. Okay. So yeah, so what is these two operations, this L reduction and this lifting representation? It's really something that goes from some representation in characteristic 0, so over K, to representation characteristic L over small k. Okay, so there is a way, you want a way to reduce mod L a representation, or you want a way to lift it to characteristic 0 when you have something of characteristic in characteristic L. And the way to do this is, as Rada explained, using this intermediate ring. When you have a representation over O, you can either extend the scalar to K, or you can reduce it modulo L to this field of characteristic L. Okay. But if you really want to go directly from one to another, then there's a price to pay, which is there is no functorial way to go really from a representation here to representation here in general. Okay, and how you do this in a non-canonical way? So you start with V, a representation over K. You can define a lattice. So some integral form which will extend to V, okay, but there is a choice for this lattice, which is encoded in the choice of the basis that Rada made yesterday. So it really depends on some choice, but you can reduce it, modulo L, to get something over a representation over K. But what matters is that whatever the choice you make for the lattice, the composition factors, so all the simple subquotients of this representation do not depend on the choice, okay? Which means that you will have a map from the Grothendieck group of your representation over K to the Grothendieck group of your representation over K. Okay, so that's the fancy way to state it, and let's call it D for decomposition. Okay, but if you really want to remember what it is, just take some lattice, you end up with some representation, and you look at all the simple subquotient of the representation together with the multiplicities, and that encodes some elements in here. Okay, so that's going in one direction, but there is another way to do it, which is dual to that reduction. If you start with a representation here, you can try to lift it over O and then extend the scalar, okay? But not every representation over K lifts to an O lattice. But there is a class of representation that do. These are the projective representation. So the projective representation too. So if you start now with something which will be a projective representation, projective rep P, so it's projective KG module, if you prefer. You can find some lattice that represents P, which will be also projective as an OG module, which will be unique up to isomorphism. And now you can extend the scalar to K to obtain a representation over K. Okay? And for the same reason that if you start with something which is irreducible here, usually you don't have anything irreducible there. There can be many composition factors. For the same reason, if you start with something indecomposable here, usually it will decompose. And what I'm interested in is really how you can decompose, given something indecomposable here, how you can decompose this one, or given some irreducible representation here, the irreducible character, how you decompose it here looking at the composition factors. Yes, thank you. Okay, so let me write this map. So again, I can use the, so let's see, approach. If I want to be consistent with these notations. So the projective modules, finitely generated projective modules, to, again, the characters, and I will denote this map by E. Okay, and one first result is that this decomposition map, so if you, oh yeah, so this is always true, sorry. This decomposition map will be surjective. This one, if the field is big enough, you field K, it's actually a split injection. Okay, so what will be the, like I said, the decomposition numbers will be my definition. So the decomposition matrix will be denoted by D, will encode how this map D decomposes. So you start with any simple module V. So V is simple over K. Okay, you decompose it, and then you can look at the multiplicities of any simple module, simple representation over a small k. Okay, so you have a matrix whose rows are indexed by irreducible representation over k, and columns by irreducible representation over small k, and that's your decomposition matrix. Okay, so that's one way to see it, but there is like a dual point of view, which will be very convenient when you want to do calculations. It's called Brouwer reciprocity. If you start with a simple module, irreducible, you can define its projective cover. Which will be projective in the decomposable module. And since you have something projective, you can look at the image of this map, which I will call the character of a PS. You can look at E of PS. So that's, whenever I will talk about the character of a projective module, I really mean via this inclusion. And what does Brouwer reciprocity tell you is that the multiplicity of S in dV as a composition factor is the same as the multiplicity of V as an irreducible character in the character of PS. Okay, so that's, yeah, just like this. It's okay here. So here, that's the usual scalar product for characters. So you look at, I mean, this character, you can decompose it as a sum of irreducible characters, and it's just records the multiplicity of V in that decomposition. Okay. So if you're, maybe I should say something, for those of you who are not really familiar with the situation of finite groups, if you work rather with the representation theory of, let's say, true algebras, or if you work with highest weight categories, that's something you should be familiar with. It's called the BGG reciprocity. If you look at the multiplicity of a simple module in a standard or in a Verma, it's the same as the multiplicity of the Verma in the filtration of the projective. Okay, so that's exactly the same spirit, this duality. Okay, so whenever we want to compute the decomposition matrix, we could either try to decompose this module, that could happen to be quite hard, or we can calculate the character, compute the character of every projective in the decomposable module. Okay, so that's actually this point of view that we're going to use a lot. Okay, so let's do some examples. So I'm going to try to stick to Rada's examples that she gave yesterday. So there were two extreme cases. The first one being when G is an L prime group. And by that I mean that L does not divide the order of G. So in that case, she said that every simple representation in characteristic L is also projective. Okay, which means nothing happens during this process. When you lift, when you take the projective cover, it's itself, then it will lift into something irreducible. Okay, and that means that the converse is also true. If you start with something irreducible and you decompose it, you L reduce it, then nothing happens. It's still irreducible. And in that case, this D is the identity matrix. So that's really the boring case if you want to do representation theory, like modular representation theory in characteristic L. Nothing happens really between characteristic 0 and characteristic L. The second example that she mentioned was the other extreme. G is an L group, which means that now L is the only prime that divides the order of the group. And in that case, so if you think about it, so she just mentioned the fact that the group algebra was indecomposable, but there's actually more to it. If you're just interested in all these numerical invariants that I mentioned, for example, the irreducible representations in characteristic L, where you don't have that many of them, you just have the trivial representation. That's the only one. So if you think about it, if you start with any vector space over FL, some extension of FL, where an L group is acting, you can always find a non-zero invariant vector. So that means that to any representation, you can always find a sub-representation, which is a line on which the group will act trivially. So in terms of representation, it means that the trivial representation is always included in any representation. So that would be the only simple representation. Okay, and every representation is built up from copies of the trivial. And although the way you glue together these copies can be very difficult, it's a problem of extension, self-extension of the trivial representation, so the cohomology of that group, which could be very difficult to understand. At the level of the irreducible representation, you don't see anything. And what is the projective cover of that representation? It's just the regular representation in that case. Okay, this one you can lift easily to the regular representation over O, which will give you over K the regular representation as well. And this, you know that it decomposes as a direct sum, where V runs over all the irreducible representation over K, and V occurs as many times at its dimension. Okay, you have something like this. So that's one way to see it. You could also say that if you start with any representation V, let's take it irreducible. What happens when you decompose it? When you do this process of choosing a lattice and reducing modulo L, you don't change the dimension of the vector space. Okay, you don't do anything for that. But then the only composition factor that you can have is this trivial, which has dimension 1. So you get as many copies as the dimension of V. So this D of V is just the dimension of V times the class of the trivial representation. Okay, and you can see now on this example this Brouwer reciprocity, because if I write the decomposition matrix in that case, will be just a column. So the rows are, as I said, the rows are labeled by things in characteristic 0. Okay, so decomposition matrix will be just something like dimension of V1, dimension of V2, and so on, dimension of Vn. Okay, so just one column. And you can either see this column has a character of the unique projective indecomposable module, Kg. Or you can see each of the row as like this L reduction of any representation V1, V2 up to Vn. Okay, and the third example, I should do it here. The symmetric group on 3 letters. So G is S3. So it has order 6. So there will be two interesting cases, 2 and 3. So if you look at the representation over K again, you have 3 representations, 2 of dimension 1. The trivial representation is noted by K. The sign representation has dimension 1, but the transposition will act by -1 on this one. And there is the reflection representation, ref, which has dimension 2. So 1, 1, and 2, and so it would be quite convenient for me to look at the corresponding Young diagram of this partition. So for the symmetry group S3, the characters are labeled by partition of 3. So you have the partition 3, the partition 1, 1, 1, 1, 3, and the partition 2, 1 here. Okay, so what happens for the decomposition matrix in that case? So of course, if L is not 2 or 3, it will be just the identity matrix. But if not, so it's D. So let's start with the case when L is 2. Okay, so the trivial, you don't have that much choice. I mean, it will reduce to the trivial. So if you start with this one, reduce to the trivial representation. Okay? If you look at the sign representation, if you work in characteristic 2, 1 and -1, they're the same. So it will reduce again into the trivial representation, dimension 1. And now if you look at the reflection representation, it has dimension 2, and 2 is also the biggest power of 2 that divides the order of G. So it's something of 2 defect 0, as Gabriel explained on his first lecture. Okay, so that means that this one will be will be single in this block, reduced to something which is both simple and projective. So you get something completely different from the rest. So we'll put a 1 here, 0 here, 0 here. Okay, so by this I mean that I have a projective indecomposable module whose character is just this one. And this will be the decomposition matrix when L is 2. Okay, what happens when L is 3? So again, the trivial gives the trivial. Now in characteristic 3, the sign is very different from the trivial, so you get another one, denoted by sign bar, to insist on the fact that it's modulo 3. And now I have to understand how this one reduces. And if you write down this representation explicitly, you will see that in characteristic 3, it will have, so depending on how you realize it, it will have the trivial representation as a submodule and the sign as a quotient, or the other way around, depending on how you do your construction. But in any case, this lattice, as I said, might depend on the representation that you obtain over K depends on the choice of this lattice. But the composition factors will not, and you get 1 copy of the trivial and 1 copy of the sign representation. Okay, so that's for L equals 3. And of course, for any other prime number, as I said, it will be just the identity matrix. So let me say a couple of remarks. So here, on these very small examples, you can compute the decomposition matrix, but this is not something you should expect to be able to do in general. Okay, so one cannot expect to compute D in general. But what we will do in the case of finite reductive groups, so we'll do explicit computation on small rank, but also try to observe some general phenomenon for big groups, for the classical series, for example. So you should rather focus on the shape of the matrix. Okay, so that's for the first thing. The second one is that one of the motivation to be interested in decomposition numbers is that because this decomposition map is surjective, it means that any simple module in positive characteristic can be expressed as a combination, possibly negative combination, of a representation in characteristic 0. And one consequence is that if you know the dimension of all the irreducible representation in characteristic 0 and the decomposition matrix, you can know the dimension of the simple module in characteristic L. Okay, so the knowledge of both the dimension of any irreducible representation in characteristic 0 and the decomposition matrix. This gives you the dimension of any representation in positive characteristic. Okay, and again, this is something you might have seen in different contexts. Again, for highest weight categories, for representation of algebraic groups. I don't know if Donna will mention that, but there is, I mean, these representations, somehow for highest weight categories, they will, I mean, the analog of this representation will be the standard or the Verma modules, for which you have character formula, like the Weil's character formula, okay, that you can compute explicitly. Then the transition matrix between the Verma and the simple can be encoded when the characteristic is not too small into the combinatorics of Deligne Lusztig polynomial, which means that there is a way, using the Deligne Lusztig polynomials, to compute a posteriori the dimension of each simple representation for an algebraic group. Okay, I'm not saying that that you can obtain formula explicitly or very rapidly, but there is a computational way to do it, and that's very important if you want to solve this kind of problems. And the last remark that I want to make is that I said that I will not be interested in any homological invariant or of the category itself, but still. So let me start by saying something about that. Is that you can have, I mean, two blocks. So I should have said that before, but if you have since if you have representation which lie in different blocks, you don't have any morphism or extensions between them. When you look at the decomposition matrix, you can restrict it to each block, and it gives you the same knowledge as the whole decomposition matrix. So somehow it's really compatible with the block decomposition. So you can talk about the decomposition matrix of a block of a finite group, and two blocks might have could have the same decomposition matrix, or having the same decomposition matrix. Are not necessarily Morita equivalent. But still, I should say, but it helps So it helps in various ways. The first thing is really related to what Rada said, is that if you can, there are several invariants, numerical invariants that you can try to bound. This one is really related to how to pass from characteristic 0 to characteristic L. There is another one which is more related to on which finite field you can realize your block. And if you can bound the two, somehow you get only finitely Morita equivalent classes with the same decomposition numbers and the same what's called Frobenius Morita numbers. And if you can do this, then that gives you an approach to solving Donovan's conjecture about exactly this finiteness of Morita equivalences of blocks given some defect. But also, if you want to construct a Morita equivalence or sometimes a derived equivalence, it helps having these numerical invariants. Because what you want to do is construct the image of projective modules or complexes of projective modules, and having as a starting point decomposition matrices that helps you to give candidates for constructing tilting complex. For example, it is things that have been done by Okuyama to solve Boy's conjecture in certain cases. And that's quite technical, but very powerful. Okay, so that's still, even though you encode only something which is very numerical, you can still deduce something about your category of representation. There are other things you can deduce from the decomposition matrix, which I won't talk about, but that's certainly interesting to look at this. Okay, so yeah, so going back to, I said that you shouldn't try to compute explicitly, but rather look at the shape of the matrix. So let's go back to that example. If you look at this one, so it's a very small example, but still you can see that there is some matrix, some square matrix that you can extract from this one. So here it's just the identity. And here it's not the identity, but it's invertible, and also it has a unitriangular shape. Okay, so that will be related to the notion of basic sets. So I mentioned already, but without being very clear, is that the decomposition matrix, the decomposition map, is surjective. So it doesn't mean that any representation can be lifted, but it can be lifted as a virtual character. Okay, so not as a representation, but as a some difference of representations. Okay, so since it's surjective, you can ask the question: is there any? So I mean, that's so the first question you would have. I mean, you would ask me. Have a positive answer. So is there any sets here so that D restricted to that set will induce an isomorphism, or a subspace so that it will induce an isomorphism? And of course that would be the case, but the question is, here you have a natural basis which is given by irreducible characters, and you can ask whether there is some sort of subset which will generate the image and also will be free, so that on which really D will be an isomorphism. So let me write it down. So that will be something that was first, I think, introduced by Hiss, as far as I know. So I should say that goes back to Hiss. Maybe that goes back to someone earlier, but I'm not so sure. But it's definitely a big part of Hiss's work. Is that a subset B of irreducible characters or irreducible representation in characteristic 0 is called a basic set of characters. If you restrict D to the span of B, this is an isomorphism. is an isomorphism. Okay, and we say that the basic set is unitriangular. So B is said to be unitriangular. If, when you look at the matrix, it's restricted to B, up to permutation, this has unitriangular shape. So you know that it's invertible, but you want it to be to have this very specific shape. So up to permuting the rows and the columns. Okay, and if I so that was should have done that. Let me just look at this these two examples. You do have a basic set in these characters. If you look at these two, so you look at the matrix, the submatrix where you restrict just to these two rows, you will see that it has unitriangular shape in both cases. So that's a very small example, and actually it will be the case for the symmetric group. I will state it in a few minutes. But it's like it's somehow one of the, when you compute many decomposition matrices and you see that most of them, they can be arranged so that you have some unitriangular parts, you can ask whether this is a legit question, whether you should actually look for something like this. And the answer is actually open in general. Let me say as a remark, is that the existence of basic sets is open in general. But we know that this unitriangular condition is too strict. That it's not always true. We have counterexamples for small blocks already. But there are counterexamples to the unitriangularity. But not in the context I will talk about during these lectures for groups of Lie type. Actually, that will be one of the conjectures that I want to talk about. The second remark is about the importance of this basic set. So since you have something which is unitriangular, you will have a parametrization of the representations in characteristic L in terms of representation in characteristic 0. So if B is a unitriangular basic set, this gives you a parametrization of here G in terms, characteristic L in terms of the representation in characteristic 0, or subset and why is this important? Again, it's somehow the same reason that I mentioned before when I said if you know the decomposition matrix and you know the dimension of these modules, then you know the dimension of these ones. If you have a parameterization like this, you will understand, for example, some properties of these characters, like the action of outer automorphisms on this representation in terms of the action on these ones. And that's, you need more to understand this, but that's really a good start if you want to deduce properties of the representation characteristic L from something characteristic 0. Okay, if you take any set, since D even with a basic set is just an isomorphism, so you know that you have the same number of elements in the basis, but you have no direct way to define a bijection between the bases. But if it has unitriangular shape, there is a canonical way to do it, and that's very important. And it also helps to, like, again, as I said with Okuyama's work, to construct some equivalences between the blocks. Once you know that you have this kind of triangular basic sets, you can expect some equivalence to have some derived equivalence to be rigid enough to be constructed directly, like combinatorially. That's what Okuyama did, and that was formalized by Chang and Rouquier in terms of this so-called perverse equivalences. Okay, but I will not talk about this. So let me just. Sorry.
So I'm asking if such a set, even maybe sufficient one such set exists, but it's not unique.
Yeah, it's not unique. Yeah, that's probably the best example is in the symmetric group. Let me say this one. So in the symmetric group, so the reducible representation that are parameterized by partitions. So you have, so to the partition n by convention, I will take the trivial representation, and to one end the sign. Okay, so there is, if you look at the Specht modules, how do I say this? The Specht modules actually give you a construction of not just representation over K, but really over a lattice over Z, which in characteristic 0 will be irreducible, will give you this ones. And in characteristic L will give you the simple modules when you look at the top. But that will give you some basic sets formed by L regular partitions. And the good thing is that it's really like in this example of S3, these two are exactly here the 2 regular and the 3 irregular. So here it happens that the basic set is global, but it won't be for various prime numbers and various symmetric groups. But the fact is, if you want to deduce from this basic set a basic set for AN, that's not the good one. It's not the good one for AN, the alternating group. So from what I understood, it's work by Bruna and Gramin, is that the way that you will construct the basic set for the alternating group is not just by restricting this basic set for Sn, which means that you have to choose another one, which is more adapted to that restriction. So it could be that, yes, there are in general several choices, and one may be better than the others. Okay. But for groups of Lie type, I will try to convince you that there is a one which is probably better than the others, as long as the characteristic is not too small. Okay, so let's I should, since I have a bit of time, I will just give you a hint of what will happen in the case of reductive groups. So that will be another example. So I will explain it in more detail on Thursday and giving you the general result. But here let me start with recalling that for G, a finite reductive group, we have these Deligne Lusztig characters, which are defined in terms of the cohomology of some varieties. So you have T, which be a stable maximal torus, I should say that GF now will be some finite reductive group. Theta is some irreducible character of the finite torus. And among them, you have the unipotent characters. So these are virtual characters, but the unipotent characters will be a subset of the irreducible character of GF, which will be defined as the constituent of the various or Tg of 1, where T runs over the F-stable maximal tori. And in that case, if you look at the union of blocks containing at least one unipotent character, okay, so you look at all the blocks of your finite group of Lie type. You restrict to all the ones which contain at least one unipotent character. These are called the unipotent blocks. In that case, as a result of Geck and Heath, is that the unipotent. So you have to assume that L is not too small. So if L is good for G and does not divide the component group of the center. So this is very small restriction for classical group. For example, you just assume that L is E is not even, it's odd. So if you assume this, then the unipotent characters they form a basic set for the unipotent blocks. And what do I want to say? And it is conjectured to be unitriangular. So as long as you have this condition of L, really the unipotent characters will seem to be this, some sort of canonical basic set in that case. But if you pass to the bad characteristic, or if you assume that L divides the order of the group, then you might need more than just the unipotent characters. You have more flexibility on the choice of the basic set, especially if you want it to be compatible with a restriction from a group with connected center to a group with non-connected center. So it gets more complicated, but at least with this condition, if you assume that the center is connected, if you're out of the small primes for the group G, you know that these unipotent characters will be somehow the only ones that you have to look at, that you have to decompose if you want to understand the decomposition matrix. And this, I will explain that on Thursday. Thank you. Yes. That's basically if you assume that's. I mean, the problem comes when L is very small, is that you can, if you want to construct these equivalences which are predicted by Brouet, you look at the cohomology of some Deligne Lusztig variety. But if you want to do it for bad primes or for primes which divide the order of the Weil group, then what you need to do is consider several complexes at the same time, and it's much more complicated. So everything that Chang and Rouquier want to apply to that context is really something generic. So where we assume that, for example, L cannot divide two cyclotomic polynomials which divide the order of G or something like this. So if you assume that L is bigger than the order of the Lie group, I think you will work in that context of equivalences predicted by Brouet. But otherwise, if the defect is non-abelian, then the conjecture of Brouet is not true, and you need to change it, and you have to play with several complexes at the same time, so it's more complicated. Yeah, but I'm talking about the different Chang-Rouquier somehow. So there is the one for which gives you derived equivalences between blocks of Sn, okay, which is coming from this SL2 categorical action. But there is the one which comes from the theory of perverse equivalences. When you go from the normalizer of the defect, the local block, you apply this algorithm of Chang and Rouquier, and that gives you a tilting complex whose endomorphism algebra should be the block of the reductive group. And that would be true only if L is not too small. Otherwise, you'd get something smaller, too small.